Well, I heard the announcement recording in progress, so that must mean it is 1 minute past 10. And we certainly won't want to start at any time different from what was announced in the chat box. I'd like to welcome Alan, Ed, John, Michael, Mitchell, Peter, Richard, and let's see, is there somebody else here? Welcome this morning, and start my video. Are we okay here, Mr. Host? Just want to make sure that everybody can see the screen and everybody can hear me. And of course, I could only ask the question, if you can't hear me, please raise your hand, but that's kind of dumb. So are we okay, Alan? Does that mean you're okay with audio and video, both the fact that you raised your hand? Okay, I am going to assume, unless I see some other hands come up or some notices, that we're okay to go. According to what it says on my screen, it says I'm screen sharing and that my audio is up. So let's get started. I'm going to talk about climate change today, and as probably you know, there's been a lot of controversy over whether it really exists. Certain folks absolutely reject the idea. On the other hand, there are something like 180 countries around the world that kind of do believe it's true, and they've signed on to the Paris Accord. So anyway, what we're going to talk about is hopefully what we can do as engineers that makes good economic sense in terms of our future care of the planet, and hopefully be something good for everybody. So here's what we want to talk about. What's going on? Is it serious? We'll look at a few facts versus fiction. What can we do? How much will it cost? We'll look specifically at greener buildings, greener transportation, greener government, and greener ethics. So some of the fiction that you probably are familiar with includes just the whole concept that climate change is a hoax, that just a bunch of people with lasers out there starting those storms. Or it's not caused by humans, it's simply a natural thing that's going on. And it's temporary, and a similar thing happened back in the 1800s when there were big dust storms for about 10 years. And folks up north notice that once in a while the temperature drops below zero. So how can there possibly, although I noticed after a recent visit to Minnesota, I don't think they had too much below zero last winter and very little snow. So every once in a while, apparently, this observation changes. And the most interesting thing I've seen is that the average temperature has not changed. So we'll maybe touch on these topics one or other, but hopefully we'll give some evidence that maybe these are fiction as to fact. And the idea that we only need to worry about sea level rise, I think anybody in Western Canada, even Northeast, I understand, has had a lot of smoke in the air lately. North Central Minnesota has a fair amount of smoke in the air from Canadian fires. So maybe there's more out there than just sea level rise to be paying some attention to. Let's first start with the difference between climate and weather. I think everybody knows, but gives me a chance to show a couple pictures. Here's a definition of weather. What is it today? And climate is the trend. So anyway, you can always look it up in the dictionary if you have one. Highly likely that maybe most people don't have dictionaries anymore. We have the web that has all that good information. But in any case, happen to have an old copy of a Webster's dictionary, and this is what they say about weather and climate. So let's get right down to business and talk about the effect of greenhouse gases. And the reason is because it's all about visible and infrared radiation. Visible light is just one form of short wavelength radiation. Infrared is a form of longer wavelength radiation. You all know that. We know that the Earth takes on radiation because anybody looking out the window probably has some evidence of that. And that night, when the sun is not shining, then when even during the daytime, the Earth actually radiates heat out into outer space because the temperature in outer space is lower than the temperature on the surface of the planet. And we know the radiation formula. So in any case, the main equilibrium, the more heat we absorb, the more we have to emit. Very simple thing. And given the rules about proportional to the fourth power of the absolute temperature, it says temperature has to go up a little bit in order to increase the emission if we absorb more heat. And the greenhouse gases reflect emitted infrared radiation back to the surface. That's called the greenhouse effect. And that's why they're called greenhouse gases. We were experiencing that in automobiles and greenhouses for a long, long time, knowing that glass will allow visible radiation through just fine, but it's not really happy to let the infrared go back out again. And so effectively, the carbon dioxide in the atmosphere and a number of other greenhouse gases, they have the same effect, or very similar effect to glass, thus greenhouse gas. And it turns out, because of this, that the amount reflected back depends upon the concentration of greenhouse gases. And if we want to restore equilibrium, then the temperature of the Earth has to increase in order to re-radiate more. Pardon me a minute. I want to move my closed captions over to a corner. Okay, so let's take a look at the radiation spectra from the sun and the Earth. All of you probably had this in physics class, who knows whatever class, but the old famous Planck's radiation law. Here we've got the sun at 5,800 Kelvin, and here we have the Earth at 300 Kelvin, more or less. And notice that there are a few orders of magnitude difference in the rate of radiation. On the other hand, the Earth is pretty far away from the sun, so we don't get the brunt of that peak radiation. Interestingly enough, this range right here is the visible. In other words, where the sunlight has the greatest intensity, that's the part we see. What an amazing thing. It turns out also that this is the part that plants like the best. Somehow or other, nature seems to have adapted to capturing and using the peak sun, the peak wavelengths, for plants and humans to be able to see things and to be able to go through their various chemical processes. Of course, the ultraviolet is below the, shorter wavelengths than the visible. We got the infrared with the longer wavelengths. And so therefore, all of the radiation of the Earth is due to infrared. And any way that we see the Earth from somewhere else is not because of its own color emission, it's because it's reflecting sunlight. And that's how folks far, far away see us at the Earth. Now, it turns out that after traveling 93 million miles, the intensity at the top of the Earth's atmosphere is about 1,367.1376665, but I left off the decimal points, watts per square meter. And once it goes through the atmosphere, it drops to about 1,000 watts per square meter at sea level if it is shining from directly overhead. If it's shining from other than directly overhead, there's going to be a thing called air mass, which absorbs more sunlight. So whenever the sun is not shining from directly overhead, it will not be shining at 1,000 watts per square meter. It'll be a bit less than that. So there's the radiation story, sun and earth. And obviously, if we absorb more of that sunlight in the infrared region, the earth temperature is going to have to go up a little bit in order to re-radiate it to keep an equilibrium situation on the surface of the planet. Very straightforward physics. So, what about atmospheric carbon dioxide? Let's take a look at it. Many of you probably already know that the Mauna Loa Observatory is pretty much recognized worldwide as the baseline measuring people. And here's what they've measured between about 1958 and about 2024. The scary part of this is there are folks who are trying to say what will happen if this greenhouse gas emission gets too high in terms of stability. And some of the observations claim that somewhere between 425 and 440 parts per million, we have possibilities for some significant problems. We're going to take a look at 11 different scenarios where this increase in carbon dioxide is kind of critical. And effectively, what we're doing here is trying to define the problem, because if you don't know exactly what the problem is, then it is pretty hard to imagine what the solution might be. So here is basically the problem: too much CO2. And if you want to read more about it, here is a very good reference, 88 pages, and I encourage anyone to get more information on this graph to take a look at it. You notice that the concentration goes up and down every year between summer and winter, because there's more absorption in the summer than the winter, because there are more sequestering agents out there to do that absorption of the carbon dioxide. So, given that, let's look at some specific tipping points that these folks for Job One for Humanity have published, and they're important to pay attention to, because normally we talk about sea level rise, but there are other things other than sea level rise. And all of these things can conceivably lead to sudden large-scale catastrophic climate changes. And this can affect human and biological systems. We're talking the possibility of irreversible global warming, at least global warming. This is the sort of thing happens if you have a meltdown in a nuclear facility. It's irreversible until you reach some certain nonlinearity, and then it stops. But until that nonlinearity is reached, the process is irreversible. And if we have irreversible climate destabilization, or extinction level climate destabilization, those would be pretty bad. And it's not real that clear. I've not seen what levels of carbon dioxide will presumably have that result. But in any case, these are things the people who work on this on a daily basis are paying attention to. Maybe not so much in the United States anymore, but certainly people around the world and other countries are paying a lot of attention to this. So let's look at the tipping points. Okay, here's the first one: total atmospheric water vapor. Boy, what a surprise. How many of you thought atmospheric water vapor might have been a problem? Just for curiosity, let's see if I'm going to drop my participant box here, and let's see if people found where the raise hand button is. How many realize that atmospheric water vapor was a tipping point? A thing of concern. All right, well, okay then, that's good. That's because when I saw this, I had never thought of it before. I thought of clouds, but actually clouds are not water vapor. Clouds are condensed water vapor. So the more water vapor is a greenhouse gas. But once it condenses and falls, it doesn't necessarily last for a long time. But in any case, when you have this high humidity, there's your example. And I'm talking to people up in New York and the Northern Tier where they're saying the humidity is unbearable right now. I'm not sure what that means in terms of really unbearable or otherwise. But so anyway, here's the numbers on it. And since anyone who wants the details, you can order a copy of these slides, no extra charge. The host will be happy to send them to you after, or maybe you've already had a chance to download them. And by the way, if you previously were able to get a copy of the slides, I had been away. I did not think I'd have a chance to update, but I found that some of the information in this presentation dated back to 2018, which is a whole lot different from what things are today. And so I have updated some of the data slides. And our host will make sure you get the new set of slides just in case you have a set of slides, but what you see will be different. So far, we're pretty much the same as we had. So anyway, here's the water vapor story. And then there's the total amount of melting ice. And that's very simple because as seawater warms, it expands, further increasing sea levels. But also, when ice on seawater melts, it produces fresh water that tends to stay on top. And so melting ice, several different ways, increases sea levels. The albedo effect, what's that? Well, that's when sea ice reflects sunlight back away from the Earth's surface. If it melts, then it doesn't do that anymore. Therefore, the sunlight that would have been reflected back gets absorbed by the ocean. And guess what happens then? What's happening here? If there's no ice, you absorb almost all of the sunlight. And of course, it melts more, heats the water, melts more ice, on, and basically an exponential process until all the ice is gone. All right. And of course, this also happens any ice that melts and is gone, but sea ice is the ice that's melting and leaving behind no ice. So far, the Greenland and Antarctica still have a fair amount of ice, so it's still reflecting the sunlight back, but that doesn't mean it's not melting fast. So, number 4, melting permafrost, interesting situation. Because there's a lot of methane trapped in frozen permafrost, and methane is a nasty greenhouse gas. And when they say 20 to 100 times stronger than CO2, the reason is because methane decays in the atmosphere, decays to carbon dioxide and water within about 15 or 20 years. So it all depends on at what point in time are you looking at the methane. But still, bottom line is at least CO2, and CO2 stays there for a long, long time until it's sequestered. So therefore, again, more melting of permafrost, more release of methane, and who else knows what else might be trapped in that permafrost, including pathogens, various kinds of germs, virus, who knows what. So this is a major concern. There's a lot of permafrost out there in Northern Tier. Number 5. No, this is not the coronavirus. This happens to be plankton. And plankton are pretty important. And one would think they wouldn't die because they're plants. And when you increase the CO2 in seawater, you'd think they'd be happy. Problem is, CO2 causes the weak acid, and plankton are not happy with the pH level of the ocean going down. So they die. Not a good thing because they absorb CO2, release oxygen, and there have been plans to dump a lot of excess CO2 into the ocean so the plankton could feed on it. But what we're finding out is carbonization, warming, and acidification of the water are not things that are that plankton are happy with. So that disrupts the food supply of fish, and it also disrupts the oxygen cycle because plankton produce somewhere between 50 and 80% of the world's oxygen supply. So another thing that this just caught me by surprise, I hadn't even thought about it, and that's why I want to share this information, because these are all things of concern. Um, some may not be terribly well documented, but none of them are mythology because they're backed by scientific evidence. Number 6, transfer of ocean surface trapped heat to lower levels. Well, if we get a circulation, vertical circulation of cold water, hot water, normally cold water goes to the bottom, but it's possible for this trapped surface heat to go to the lower level. And what did I do? Oh, sorry, I'm moving my clicker the wrong direction. Maybe I can do a different way. No. We do that. The densest water is the reason it sinks to the bottom is because cooler water is denser and it sinks to the bottom. We do know all about that and water heaters and so forth. But when it does circulate to the bottom, then you cause a more rapid rise in surface temperature. And that is, again, is an exponential process. Number 7, loss of forest. Don't have to tell anybody about that. If you get rid of those green trees, then the absorption of CO2, it's more difficult to recombine. So that's a problem. Number 8, release of carbon from soils. Another one that came as a surprise to me. I hadn't thought about that. But when they dry out, the carbon can be released. And soil normally stores it. But if it gets hot, then it will release it in the form of carbon dioxide. And again, exponential. What's the next one? Number 9, changes in major ocean currents. There is some evidence that the Gulf Stream is slowing down, for example. And when that happens, then if the Gulf Stream slows down, that can change the path of hurricanes. And I know that right where I live here in South Florida, we used to be major targets, but the most recent ones seem to be more happy to go into the Gulf and then go back across Florida from in the Tampa to Jacksonville path. So I don't know if that's a permanent thing, but that seems what's happened with the most recent hurricanes, and the folks up in the middle of Florida are not all happy about that. Changing ocean currents. All kinds of things can happen when ocean currents change. So again, something we can maybe be concerned about. Potential for global pandemic. Because who knows what's in the permafrost. So again, as we mentioned earlier, could be a problem. Total weight of rising seas and melting ice shifting. Well, what about the Earth's crust? As it warms up, there's this coefficient of linear expansion. Not very much. On the other hand, if you're doing that over distances of tens of thousands of miles, a few fractions of an inch per inch becomes a few feet or a few half miles or something. And if those various plates can't slide over each other properly, you get something like the most recent earthquake that was just been announced in the up near the Aleutian Islands in eastern Russia. So interesting thing. There's the tectonic plates thing, earthquakes, volcanoes, tsunamis. I haven't heard yet whether the tsunamis from this earthquake, how significant they've been. But a supervolcano is pretty serious business, and the planet has already done that experiment. So 11 tipping points. There maybe have been some others, but I just wanted to point out that sea level rise is not the only thing that's going on out there. So let's take a look now at some of the numbers. Between 1990 and 2022, these are, wow, I woke up sneezing a little bit this morning. I apologize. They come on so fast. I either have to grab for a Kleenex, one hand mute myself and the other grab for a Kleenex. So I hope you'll excuse me if I sometimes grab for the Kleenex first. In any case, this is the all kinds of CO2 and COQ equivalents. But also the important thing is we've got total emissions in the bar and from various sources. And it's interesting to know how much is from the lesser known greenhouse gases, like nitrous oxide, methane, the sulfur, hexafluorides, nitrogen, trifluorides. I don't even remember HFC, fluorocarbons. Yeah, fluorocarbons. So, and then the carbon dioxide itself. Now, the other purple at the bottom is kind of important because that's the sequestration rate. And so when you subtract the sequestration from the emissions, from the total, you get your net emissions. And notice that here's really the problem, because we say if we just get rid of production of carbon, if we go carbon neutral, then we solve the problem. Well, carbon neutral doesn't quite solve the problem. We got to go carbon negative, carbon dioxide negative, because we are exceeding the sequestration rate by about a factor of 8. And notice also that between 1990 and 2022, thanks to cutting down trees and things, that sequestration in 2022 is actually lower than it was in 1990. So pretty clear definition of what's going on out there in terms of what's going on, what's going up, and what's getting sequestered. So once again, data, what can we do about it? Here's your resource on it. So what about comparison between 2018 24 electric utility generation? Because one could argue that all CO2 is coming from the electric utilities. Let's just do a little comparison. And here's the generation by source in 2018 and 2024. 2024 is broken down a little more. Renewables was included hydro back in 2018, but we're breaking now in 2024 the non-carbon dioxide producing sources, except for nuclear, into wind, hydro, and solar. So what we have here is in 2018, generation of 421 or 4,125 billion kilowatt hours of electricity, a slight increase between 2024 and 2018 in electrical generation, but a 25% renewable generation in 2024, and that includes hydro. So what's that mean? Well, it means that why? Oh, all right. I'm sorry. That is the data. I thought there were some other notes to be showing up on the bottom, but I'm wrong with that. So anyway, this is the mix as it's changed. You notice that coal has dropped from 1,146 billion kilowatt hours to 710 because the utilities have been rapidly replacing coal with natural gas and with renewables. That's what's been happening. Who knows what's going to happen in the next few years? But that is what happened between 2018 and 2024. What about CO2 production now by the electrical generation sector? We already know that they made more electricity. How much CO2 did they make? Well, let's take a look. 2018, 1.77 gigatons, and that was the mix of fuels. And here we are in 2024, coal, natural gas. No, these are not the source of the power. These are the source of the CO2. Notice that the nuclear and the renewables are left out of this picture because they do not generate CO2 when they're making electricity. So, and notice that the amount of CO2 from coal has dropped significantly from 65% to 53.1%, but the amount from natural gas has gone up to a higher fraction of the mix. And other things, what would this be? Well, there are some diesel generators and things out there, but they're less than 0.5%. So the total, though, in 2024 was 1.34 gigatons, which happens to be 24% less than 2018. So the utilities have been doing their job. They have been reducing their production of greenhouse gases fairly significantly. And their plans, because of economics, the cost of making electricity with wind and solar and geothermal, and using storage is dropping below the cost of making electricity with other sources. So it's very economically attractive. That's what the utilities have been doing over the last 6 years, 7 years. So just useful information. What about by sector? Where is it being generated the most? Well, electric power, 29.7%. Transportation, 38.6%. Residential, 6.5%. Commercial, 5.2%. Now, keep in mind, the electric power people make electricity that everybody else uses. So therefore, the 6.5% is from the use of carbon dioxide emitting fuels, in addition to whatever electricity is being used by the residential, commercial sector, or transportation sector. Of course, right now, the transportation sector is using mostly fossil fuel, but there is some change going on with the advent of electric vehicles. And here's the industrial. We're at 20% for industrial. So industrial, they burn a fair amount of coal and natural gas for heat processes. And but the biggest contributor is transportation. So, when you're trying to solve a problem, you want to look at, well, probably which is the most economically feasible to approach, but also where are the biggest contribution versus other places. So 2023 total, 4,807 million metric tons. 2019, 5,147. So in fact, 2019 was actually 7% higher in production than 2023. So let's look at what's happening worldwide. I know this is supposed to be a climate change. Well, yeah, what we're doing is defining the problem. And here's what's been happening in terms of the use of primary fuels. Now, primary fuel means coal might have a certain number of BTUs or kilowatt hours of energy in the coal itself, but the amount recoverable when you burn it, thanks to the second law of circular thermodynamics, is oftentimes only about 40%. So this is the total energy of the source not the actual recoverable energy necessarily. Now, for example, with natural gas, we're going to look at some of the numbers on these in a minute when we look at zero energy buildings. So in any case, the question is, where are we going from 2023? And the trends are very interesting. Notice the green line. Notice them all. Notice what happens by 2028 if we keep on the same track, which we may or may not do. But if you add the green and the blue and the orange, the nuclear, the hydro, and the wind and solar and geothermal, the sum of those three by 2028 gets right up there in the neighborhood of the amount of energy, primary energy available from the fossil fuels. So then the question is, if we don't consume a whole lot more energy total, will these other three sources start replacing the fossil fuel sources? Will that happen? Because they all add up to the total energy we use, but notice there's a logarithmic scale over there on the left-hand side, so you got to be careful with the numbers, but still, in right around 2030, some interesting things should happen. And that's why I'm working with a personal trainer to try to stay alive for 5 more years and see if this curve is works properly or not. So in any case, it's interesting. I started first drawing this curve back in about 2014. And it's interesting how the projections from 2014 have been pretty close. And so now the question is where the big difference can happen up around 2030 to 2035. Is it going to happen or what? Can we afford it? So let's take a look. There's some of the numbers on the bottom there. And 18.7% of these sources in 2024 or 2023 are not producing carbon dioxide. And notice where the source of this, British Petroleum, started collecting this data way back when, and now the Energy Institute has taken over from them recently, the last few years. But this is oil company data. So presumably that would be fairly reliable. And nobody's argued the point. So anyway, we got some numbers. Again, baseline data that we can be using as we develop various scenarios. So for example, if we do the following scenario, equal annual energy or percentage reductions in all sectors with a 2% annual population increase, okay? If we do it with an initial decrease of 2.5%, and then every year following, we add 15% to that 2.5%. So in other words, the first year decreases 2.5%, next year 2.875%, next year 3.306%, and so forth. Whether these numbers are realistic, consider the fact that China, in I think it's either 2023 over 2022 or 2024 over 23, I don't remember which, their production of electricity by photovoltaics increased year over year. The installations increased year over year by 150%. So is 2.875% possible? You bet it is. Now the question is, what's it going to cost? So, but notice that if we follow this scenario, and this is, whose scenario is this? It's mine. I mean, I know math. I'm allowed to do a scenario. You can do one yourself if you want to. Make your own assumptions. I thought this was pretty conservative, and that's what I wanted to do. I wanted to take into account population increase. The only thing I didn't include was changes in government. That can have an effect, maybe. But this is United States, and the rest of the world is still out there, and they are still following the Paris Climate Accord. And China and India and the European Union in particular are all working on it really hard. So whether or not we do this, everybody else is going to probably be doing this because it's a reasonable scenario, and we'll show how the economics work. In fact, we'll show these economics right now. First transition, we have to get rid of the coal because that would be 1.15 trillion kilowatt hours a year with renewable generation, and the natural gas, 1.47 trillion kilowatt hours with renewables. And then, strangely enough, the sun doesn't seem to shine at night, no matter how hard we try. So therefore, we're going to have some energy storage, and in order to ensure system stability. And it's estimated by the folks who do this kind of work that we'll need about 100 million kilowatts. Now, one would argue 100 million kilowatts. What about kilowatt hours as energy? Kilowatts is power. Well, that's nighttime power demand is 100 kilowatts we're going to need to pick up. And with enough hours to meet that 100 million kilowatts. So if we, so the next thing is we need to, well, let's talk about eliminating coal. And the cost of that, and if you go through the math, it would be about $2.15 trillion in today's dollar. And if we did that equally over 10 years, it's about $215 billion a year. All right. If we then do the same with natural gas, we're looking at about $275 billion a year for a period of 10 years. And so 215 and 275 is $490 billion a year. How much money is that? Well, the United States gross domestic product a few years back was 22.8 trillion. It's closer to 28 trillion now. And the United States annual military budget is 700 billion, and they're planning to increase that. And this is all taxpayer money, whereas these 275 billion or 490 billion we're talking about, good percentage of that comes from investors, not from taxpayers, not subsidies or whatever. So economically, this transition is very attractive. And guess what? These are the numbers the utilities are looking at as they move to wind and solar. It was very interesting a couple of weeks ago driving through the state of Iowa, looking at all our windmills, and Oklahoma windmills, lots of windmills in certain areas of the country where there's enough wind, and solar everywhere because everybody has sun. So bottom line, it's affordable. And of course, that's going to require a fair amount of engineering to make this happen. And guess who's going to have to be responsible for that? What about storing energy? This happens to be what you see right here is a 100 megawatt, 127 megawatt hour energy storage facility that was completed in 2017, later 2017 in South Australia, because they had some instabilities in their production facility. And it was built in less than 100 days, bottom line. So other storage, pumped hydro, that's been around for 60, 70 years because we started doing that when nuclear wanted to be run at a constant rate of production to prevent it from either shutting down or melting down. But if you keep the production rate steady, if you find a place to use that electricity, then the nukes work fine. So pumped hydro was introduced a long time ago. We've got a lot of it out there. Compressed air, it's more or less economically feasible, but there are only a couple of sites that are economically, there's one in the United States and one in the desert somewhere in Africa, I think it is. There's capacitors, flywheels, at least 10 different battery technologies. In fact, it's possible to use excess electric vehicle battery capacity. We have a separate 2-hour webinar on that. And lifting weights is another similar thing to pumping hydro, but doesn't take nearly as much space. The only thing is you got to be careful what weight you use, because if you use concrete, the energy intensity of concrete is almost greater than the amount of energy that you can store. But folks over in Europe are exploring other materials where you don't have to use a whole lot of energy in order to create the weight that you want to lift. And you can imagine it's just like pumped hydro. Instead of lifting water, you lift some other weight straight up vertically and straight down. And they're doing this with nice large buildings. You can Google it and see examples of some functioning lifting weight facilities in Europe. Anything that's commercial implies it's cost effective, because people don't like to make an investment unless they can get it back. So present storage cost is something like 125 US dollars per kilowatt hour. Now, this is maybe a little bit misleading, because the question is, what form is this kilowatt hour in? Is it in potential energy of water? Is it in DC batteries, which has to be made from converting AC to DC and then DC back into AC? These add some additional cost, but the storage cost itself is in the neighborhood of $125 per kilowatt hour, and it's been dropping because there's been a lot of excitement about storage recently. First 100 years or so, lead acid batteries did the job. Who needed anything else? And a little bit of pumped hydro. But now there's a lot of excitement. And the other thing to note is that storage has a kilowatt and a kilowatt hour component, because it has to be able to provide the instantaneous energy. That means it has to be able to discharge at a predictable rate, and it has to have enough energy available such that at the rate of discharge, it will still have that energy over the period where it's needed. So large energy storage facilities, or even smaller ones in the neighborhood of 5 kilowatt hours, 10 kilowatt hours, 13.5 kilowatt hours, kind used in typical residential storage. They also include how many watts can you get out of this thing if you want to use it as a backup. So 1 megawatt hour means it'll deliver a megawatt for an hour. Here's a few examples of storage. Believe it or not, the one in the upper left is pumped hydro. The thing in the lower left may not be obvious, but that happens to be a flywheel. And the one with the walkway in the lower is a liquid battery, because if they leak, you don't want to be walking through it. And then you've got your lithium storage in the upper right. So all of these have been demonstrated to be commercially feasible and have different uses. What did I do? How did that happen? Oh, we're trying to find a call. I've got to get a new mouse, I guess. It's a little touchy here. 4 hours at 100 million kilowatts is 400 million kilowatt hours. Okay, 4 hours. So at $125 per kilowatt hour, that's $50 billion. You keep in mind now, this is available on a daily basis. Charge, discharge, charge, discharge. However many cycles it might be rated for. Maybe it's rated for 3,000, 9,000, 10,000, or 50,000, depending on the technology. So you have to distinguish between storage in terms of total kilowatt hours used in a year versus the daily amount of kilowatt hours, and how many of those daily kilowatt hours need to be stored in order to be available when people want them. All right. So in the past, that pumped hydro was available at night when the nuclear people needed it. Daytime now, that same pumped hydro is available when the solar and wind and renewable sources are making more than the grid needs. And rather than curtail them, since the fuel is free, it makes better economic sense to store the energy. Even if the round trip efficiency is 80%. It's still better than the curtailment. So overall, there will be long-term and short-term storage. And here's the terms: it can be local, neighborhood, regional. Electric vehicles can be a major contributor to storage. If you have 100 million of them, each one can give 5 kilowatts and 5 kilowatt hours a day. That's 500 million kilowatts and 500 million kilowatt hours. Now, it's not likely it's going to be like this, be 100%. On the other hand, there's a possibility that we'll have more than 100 million EVs, because right now there's something like 285 million vehicles out there that may at some point be replaced, because people like EVs. Every EV owner I've ever talked to loves it. And I happen to own a plug-in hybrid, and we're crazy about that car. It's the best car we've ever had. We don't drive a lot, and so mostly we can get by driving it electric only at 8 cents a kilowatt hour, which equates to less than $1 a gallon if we were to use gas. So we're going to see things happen with EVs, whether or not they're simply contributing to load management or whether they're actually selling back to the grid. They have that potential. It's a matter of whether we choose to develop it. It's available, the codes are there, the standards are there, and for that matter, the Cybertrucks are there, all set, ready to go to sell back to the grid if somebody wants it. And we already mentioned the technology is developing rapidly, costs are declining, just as most of the other renewable costs have been going down. So there's some background. Now let's look at some on the other side of the equation. All right. In other words, reducing the amount of energy used, because the economic choice is going to be a balance between should we use less or should we generate more with less expensive sources, which is more cost effective. And of course, this is going to be an interesting engineering analysis. What should we do? How should we build this thing? How should we build this house, this building, this car, this airplane, whatever? So let's look at the definition of a zero energy unit. And what we have to start with is a site boundary. What do we got for time? 10:53. Okay, we're coming along okay. Should make it. And by the way, I meant to say, if you have any comments, any questions, I tend to get kind of immersed into what I'm talking about. And if I don't see you raise a hand or something in the chat box or in the participant box, then all you need to do is turn on your microphone and say, hey, Roger, can you hang on for a minute? I have a question. And I respond very well to that kind of a question. Even if it's, hey, idiot, you're going too fast. I can do it that too. Because my job is to present to you something that makes sense, something you'll find useful, and something you won't regret spending 2 hours getting the continuing ed credit for. So don't hesitate to break in at any point if you have any questions or comments. All right, so we have a site boundary. Inside that site boundary, we're going to have a building, a campus, or some kind of a community energy use thing. Maybe it will just be one building, or maybe it will be a neighborhood, whatever. But we're looking at a zero energy unit. All right. Now, what are those arrows all about? Well, first of all, you're going to have to produce some zero energy or zero carbon energy on site that will be used by the building. And then you're going to buy some energy from somebody else, utilities, whatever. And there might be some renewable component in that. And then you're going to sell some back, because you won't be using all of the renewable energy you produce every minute of the day. So you will be selling it back. And the key for zero energy is that the delivered energy equals the exported energy. It's not that you don't use any, it's just that you make up for the energy that you use by making energy yourself and selling it back. The same quantity, usable quantity, as opposed to primary energy component. And we're going to see that here in just a minute. What does that mean? Okay, so we have to have source energy conversion factors because we recognize that earlier that coal, if you burn it, you don't get all of the initial BTUs from it. Now, if you're using that coal to melt iron or steel, that's one thing, but if you're using it to make electricity, it's a different conversion factor for the usable electricity versus the available electricity. So the conversion factors that have been adopted and agreed to are for imported electricity 3.15. And that's the idea that the import electricity is probably mostly fossil, which is not necessarily the case now. But if in fact imported electricity has a factor of 3.15 source energy conversion factor, then it's only fair that if you're exporting renewable electricity, I mean, the wires can't tell the different colors of the electrons. So the exported should also get a 3.15. Natural gas is 1.09 because on a water heater, they're pretty efficient, about 90% efficient of the heat you burn. 90% of that actually goes into the water. Fuel oil, diesel, kerosene for the applications, slightly more losses there. Propane and liquid gases, slightly more losses, but mostly it's for heating buildings, and most of the heat is retained. It's not converted into other forms of energy. Steam, hot water, chilled water, and coal or other, the source energy conversion factors. Okay, so if you're just burning coal to heat stuff up, you get most of the heat from it. But if you're making electricity, that's another story. So these factors are agreed upon by the folks who do the zero energy stuff. And so if we want to estimate the direct building energy usage, it might go something like this. You have to convert it to source energy. Okay, so if all energy is converted to BTUs, that's convenient. So let's, here's a few conversion factors. Kilowatt hours, 3,413 BTUs for 100% conversion. A therm gives us 100,000 BTUs of heat. Barrel of oil is 42 gallons. That'll give you 5,800,000 BTUs of heat of source energy. And a gallon of fuel oil is about 137,400 BTUs. So these are convenient conversion factors into source energy. So you need to make a list of the energy sources and then convert them. Okay, so let's do it. Let's assume this building that suffered a little damage from a fire is rebuilt as a zero energy building. Let's assume that it would use 7,500 kilowatt hours of electricity and 500 therms of purchased natural gas. Let's now, if that's the case, we have to convert our electricity into BTUs. We have to convert our natural gas into BTUs. So here we have a total BTUs plus therms is 135,132,125 BTUs of source energy. All right, this is per year. All right, so now all we have to do is figure out how do we offset this with renewables or whatever. And we'll do it with PV simply because that's what I do in my spare time is I sign off on PV systems. So, but you know, you can do wind or whatever, but if we want to just estimate whether this is realistic to do it with solar, and that's the whole idea here is this a possibility? All right, so let's see what happens. How much solar does it take to provide this 135,132,125 BTUs? I left off after the decimal point of source energy a year. Well, that's pretty straightforward. With an unshaded south-facing array, you could expect it to produce somewhere in the neighborhood of 1,500 kilowatt hours per kilowatt per year. And that depends on the location. So if we convert the BTUs to kilowatts per year, that gives us 5,119,500 BTUs per kilowatt per year. And by the way, to find the exact numbers here, the National Renewable Energy Labs has a program, which I think might still be available, although they laid a lot of workers out there. But there are commercially available programs as well, where you can just tell the program where you're located geographically, what direction is it facing, and what's the roof tilt, and it will give you an estimate of your annual kilowatt hour production. So this is done routinely by those who design solar systems and market solar systems in order to get some idea what the payback is. So here's how much we need to produce. Here's how much will be produced by every kilowatt. So we know how many we need. Well, wait, no, we don't, because we have to convert this to source energy in order to be fair. So this gives us then 16,126,425 BTUs per year per kilowatt to put it on par with the other sources that manufacture electricity. And so now we look at this 16 million and compare that with the annual need, and we get 8.38 kilowatts. Well, I can tell you from experience, I've looked at over 7,500 residential systems, and the average system that we've been seeing being designed and installed here in South Florida is about 11 kW. So that gives a little bit to spare. So 8.38 kilowatts, how much space does it take anyway? Well, 20% efficiency is pretty common. So that would mean 200 watts per square meter at standard test conditions that can be produced. And 8,380 watts divided by 200 watts per square meter, 451 square feet of south-facing roof space. If you got east, west, north, you can add to that, and the losses for those directions are somewhere in the neighborhood of 15 to 30%, which means you need a little more space on those roofs to make the electricity. But a northeast facing roof in the summer does fairly well, actually, because especially up north, where the sun rises very early in the morning from the northeast, and it will be shining right on that array, making lots of electricity as soon as it comes up in the morning. And same thing at night with northwest. So in any case, south-facing 451 square feet, more than that if you're on other roof planes, but it's realistic because people are doing it. If you use 300-watt modules, and again, that's a small module because typical module now is more like 420 watts, but 28 300-watt modules, and check the dimensions of the modules and the roofs to see how well it fits, and you'll probably figure out a way to do it. So it's possible. Well, let's turn to HVAC. What's out there? Well, we got these now. And with these mini splits, they operate down to 13 below Fahrenheit, SAER up to 33.1. This is one I didn't update. I've seen SAERs advertised for mini splits now with 38 or more. That's pretty high because back in 1980, when the first energy efficiency for building construction codes came out, the minimum SAER requirement was 8.0. So we're looking at efficiencies are 4 times as efficient. HVAC systems are 4 times as efficient as they were 40 years ago. There's other things out there as well. There are these things, the energy recovery ventilators. Some of you might be familiar with them. In fact, let's take just a minute here. I'm going to look at my participant box again. If you're familiar with any of these, in addition to the energy recovery ventilation, we got heat recovery ventilation. How many of you are familiar with any of these particular technologies? Let me find my and look for hands. Now we got John, Ellen, John, and not sure whether Ed, Michael, Mitchell, Peter, Richard, and Richard are able to raise their hands or not, but at least a few of you are familiar with these technologies. The mini split, no ductwork. That item up in the top left-hand corner, that's your handler. And it's connected to the outdoor unit, the condenser unit with the refrigerant lines. So no ducts, just refrigerant lines to the units. Well, it's kind of like a window unit. It's not like a nice clean duct, but then again, when you look at the efficiency, I was recently up in Canada, and these things are taken over like just all over the place. You see the outdoor compressor units for mini splits. Very, very popular. Energy recovery ventilation is simply a counter-current heat exchanger, so that, you know, if you turn on your bathroom vent fan, you're blowing heat out, or you're blowing conditioned air out, whether it's heated or whether it's cooled. That has to be made up. So where does it come from? Outside. Well, if you have a counter-current heat exchanger, then it will do heat exchanging, either of heat or cool, with the makeup air and the exhausted air. Energy recovery simply means that it also takes into account humidity, and if the air coming in ends up needing to be condensed with humidity, it means simply you need a condensate drain on the energy recovery ventilation to keep the humidity of that hot outside air coming in, hot, humid outside air. Of course, nobody ever sees any of that except all of you up in New York right now. The heat recovery ventilation, if you don't need to worry about humidity control, that's slightly more simple because you don't need to have a condensate drain. So anyway, these are some of the building systems that can be used to make these zero energy buildings. And what do? Well, what's the cost to do one of these versus adding extra solar? What about domestic water heating? Well, you just compare the lifetime cost of electric water heaters or natural gas water heater versus solar water heating. And solar domestic hot water was really a good deal. Even 10, 20, 30 years ago. But now there's another kind of water heater out there called a heat pump water heater, which is also called a hybrid water heater. And they can produce about 3.5 kilowatt hours of heating for every kilowatt hour of electricity used. In other words, coefficient of performance of 3.5. Now, they're called hybrid heaters because the rate of production of heat could be a problem if you needed a lot of hot water in a hurry. So they still connect up your same 30 amp circuit so that they have a backup electric element, 4,500 watt electric element, just in case you want hot water in a hurry. And that's why they call them a hybrid, because hopefully if you schedule your water use, most of your hot water will come from the heat pump, and only a small amount of your hot water will come from the direct resistance heating. These things, if you do the math, for somebody living 24/7, or especially if somebody is a seasonal resident, a solar water heater for a seasonal resident, when you're not using it, it basically shuts down. But if you have solar PV to make the electricity for a heat pump water heater, that solar PV, when you're not there, it can be sold to the grid, whether you're there or not. So do the math and see how it looks. And it's highly likely now. And I've got a lot of friends who have been in the solar water heater business for a long time. But these hybrid water heaters are now for uh, especially for seasonal use, generally come out looking a whole lot better than a straight solar water heater, even though the solar water heater can have a pretty high efficiency of heating, much more than 20%. But when you take that 20% PV conversion and then multiply it by 3.5, which effectively you get with the COP, all of a sudden that exceeds the efficiency. So anyway, something to think about. This is what they look like for a 40 gallon. That black part on top is the heat pump part. The only possible drawback, and something that caused me to think twice and decide to wait till I have better information, is if you live in a condominium or a building where that thing's going to be stuck in a corner with very little ventilation, and you'd have no way of venting that cool air that comes out of it, it's possible you might have some mildew growth. But if that's out in the garage, after all, what are you doing to heat that water? You're taking heat out of the air, which means it becomes an air conditioner for the time that it's running. So it also can contribute to lowering your air conditioning bill. Very interesting machine. And they're starting to, people are starting to become aware of these things. But I'm surprised that they're not picking up as much. The marginal cost is somewhere around $700. The payback on that's maybe 5 years, depending on the condition. Again, something a good engineer can easily do the calculation. What are the trade-offs? Well, more efficient appliances, smaller solar. So you just compare the cost. Greater efficiency with the renewable cost of adding renewables. And anyway, we've talked about that and talked about that. And then again, there's an electric vehicle or two as part of the building load. So it turns out that maybe another 2 kW added to your array will provide all the electricity you need to charge your electric vehicle. Again, it depends how long you drive it. But again, those are numbers that are easily calculated. So it's interesting to look at our array orientations, and let's just look at Albany here. And notice that the optimal tilt for Albany is 30 degrees. It faces directly south. And there you get 100% of your available energy. But look what happens if you tilt it up to 45. You only lose 1%. If you tilt it up to 60 degrees facing south, then you lose 7%. And you can see the numbers there. Southeast, southwest. I don't have a northeast and northwest, but those numbers are realistic numbers as well. Somewhere in the 70% ranges. So once again, you can use these numbers to compare the economic viability or desirability of adding solar panels in those particular orientations. A study has been done to compare the additional mortgage costs for building a zero energy building versus the savings in the utility bills. And here's the result. Very interesting. If we look at Atlanta, it costs an extra $19,500, increase of 100% on a mortgage. And again, this is depending on what the mortgage rate is and so forth. So you need to use present numbers here. And the monthly energy savings might be different now because the electric rate may have gone up, whatever. But in any case, this is the result of the study that was done back somewhere around 2019. And the results in general are better now in 2025 than they were in 2019. But even 2019 is pretty impressive because for an extra mortgage payment of $91 in San Francisco, you're saving $217 on your energy payments. And by the way, that is a non-taxable savings fee. So that's any other savings account, the interest you get on your savings, you're going to pay tax on it. But here's a savings you don't have to pay tax until they find out about it. So let's be very quiet about that. Okay, energy efficiency retrofits and electrification. Well, yeah, obviously. Just some of the things can be done. Lots and lots of work for engineers. All this stuff can be done, most of which is cost effective. But again, you run the numbers. What are the comparisons? LED lights, most everybody's already done that. They realize it, so totally doesn't make sense to go with incandescents anymore. Water efficiency in landscaping. I mean, there are systems, landscaping systems that are so efficient they can tell what kind of soil you've got, whether it's in the shade, what time of year it is, what's the temperature, and regulate the water and save up to 70–80% on total water use for landscaping. And of course, then there's also putting in plants that are more native and rather than just planting grass. So they're cost effective. They're things to look at. There are computer programs out there. Here's Energy Gauge USA. Okay. And this is a screenshot. Energy Gauge is from the Florida Solar Energy Center. National Renewable Energy Labs has building energy optimization and that's good for single family or either new or retrofit analysis. The Florida Solar Energy Center Energy Gauge has two versions, one for residential, another one for tall buildings. So you can get them on trial basis for 30 days. If you like them, then I'm not exactly sure how they're charging for them now, but they're trying to recover some of the effort they put into creating them. And of course, I mentioned earlier, the National Renewable Energy Laboratory System Advisory Model. It's a free download, or at least it has been. I haven't tried downloading it recently. And if you can't get SAM, there are other folks out there who have written programs for analyzing photovoltaic systems. Let's talk about vehicles and fossil fuels. Let's let Roger take a look at his clock here and see how we're doing. 11:18. We're more or less on track. What about those vehicles? Remember, back there, vehicles are a major contributor now, the major contributor for single source of CO2. Let's put some numbers down here. Gallon of gasoline releases 19.6 pounds of CO2. Coal-generated electricity releases 2.2 pounds of CO2. Natural gas-generated electricity, 0.9 pounds of CO2 per kilowatt hour. Why are the utilities transitioning from coal to natural gas? Well, a lot of them have found that natural gas is easier to work with than coal. And some of them are actually feeling that, gee, maybe this is a good idea. And that's, you saw the numbers earlier from the transition from coal to natural gas. And of course, renewable releases 0 pounds of CO2 per kilowatt hour. And of course, everybody's going to say, but wait, wait. You got to talk about the CO2 and mining all that silicon and stuff like that. Well, yeah. And then there's a thing called the energy payback time. And for most of the renewable technologies, you pay back the price of the CO2 within 3 years. And most of the renewables are guaranteed for at least 25 years. So for the first 3 years, you saved the amount of CO2 that was used in creating the equipment, creating and installing the equipment. And for the next 22 years, you're home free, because from that point, no more CO2 release, because you're using a fuel with no cost. Problem, of course, with solar is it's only going to last for another 4.5 billion years. And then we have to start thinking about another replacement. But 4.5 billion is good enough for me for the moment. And I'm confident that folks, when we reach that point, will give some serious thought to what they're going to do about it. So let's see, what else? Gas cars, about 25 miles per gallon. That means 80 pounds of CO2 for every 100 miles driven. Electric cars get 3 to 4 miles per kilowatt hour. So if you have electric cars using natural gas generated electricity, then they release about 25 pounds of CO2 per 100 miles driven. So 25 instead of 80. Now, actually, in some areas where there's a fair amount of nuclear and renewables, the CO2 produced by the electric utility per kilowatt hour is actually less than the natural gas number. And because they're mostly natural gas plus these other nuclear and renewable and almost no coal, so they're down to about 0.92. And I mean, below 0.9. And so we've got almost a factor of 4 difference in the amount of CO2 between gasoline and electricity that's generated partially with fossil fuels. That doesn't talk about maintenance and other things either. We're just talking fuel costs. If we convert that to dollars, it's the equivalent on average about less than $1 a gallon for the equivalent electricity to run a car. Of course, if you generate renewable, because if you have extra solar at your house, you can charge your car. You can even have your solar system set up with an electric vehicle charger such that anytime you have excess, it'll go to charge your vehicle if it's plugged in. So then that's really fuel efficient and CO2 efficient. Do a comparison. There's your EV. And again, if it's 100% renewable electricity, then you're looking at about $450 fuel costs for 10,000 miles. If you have a gasoline vehicle at 25 miles per gallon, then that's 400 gallons of gas. At $3 a gallon, that's $1,200. At 4, it's $1,600. It all depends on what gas price is. I see it's around $3 a gallon now. I drive a plug-in hybrid, so I don't buy it very often, and the fuel costs fluctuate significantly between the 2 times a year that I buy fuel. But somewhere in the neighborhood of 1,200. 7,840 pounds of CO2, which is 3.56 metric tons. And still, $1,200 at $3 a gallon is a lot cheaper than, or is a bit more expensive than 450 at no gallons used. But in any case, if we look at all the 275 million vehicles on the road, then that adds up to an incredible amount of CO2 release, and that's where that percentage comes from that we saw earlier. So it's highly likely that whether we do it or not, we know for sure everybody else is going to be converting over to electric vehicles. The Norwegians, that's all they sell over there now is electric vehicles, and they've got a lot of hydropower there, so their electricity is pretty green, so they're wanting to make use of that with electric vehicles. And other countries are following Norway's lead. And even the United States, it's projected that we're still going to be buying electric vehicles because that seems to not be a major political issue. There are people on both sides that find that they really do like their electric vehicles. So there's more than just cars out there. There's buses, electric buses, school buses, local transportation, trucks. A lot of these driving around my neighborhood these days. I'm not sure about yours, the Cybertruck and electric trains. So we've got them already. So there's smaller stuff too. Any university town, you got lots of these around, and maybe some of these, not so many in the United States, but in other countries, there's lots of these. Same with these. Harley Davidson loves these because it's quite an interesting situation when one of these is up against a Harley and smaller bin. So in other words, there's a lot of smaller stuff, and I didn't even show the scooters and the unicycles and stuff. And again, in my neighborhood, we see quite a few people riding around that kind of stuff. So we didn't count this in the renewable energy that we might need. What if we have 275 million EVs? How much more renewables will we need? Well, not too hard to do the calculation. Should cost about 1.3 trillion. And maybe less since costs are coming down. So that's 1.3 trillion total, which is 130 billion a year over 10 years, which is peanuts compared to other expenditures. And it's ballpark, because the other thing is we may not need that much more electricity. They've done a lot more interesting estimates now. Estimates that the data centers are going to be the major requirement for new electricity over the next decade or so, or at least the next 5 years. But energy efficiency is going to free up some of the kilowatt hours. And so maybe it won't cost that much to power these electric vehicles. What other challenges are there to the grid? Well, storage, of course. But there's lots of possibilities. Have to be careful because we need to recognize that generators don't like power sources, other power sources, trying to send electricity back to them, because then they become loads, they become motors, and they don't like that. The prime movers don't like it. So the total generation has to be regulated. It has to be stored or something so that it won't go back into the primary prime mover rotating generation equipment. Another thing that's an interesting possibility is voltage amplitude stabilization at substation levels. May have to replace mechanical transformer voltage taps. On the other hand, it may be that this may not be an issue, because with proper load management, and that meaning curtailment of loads plus using storage to beef up the grid, it's possible that substation levels at the distribution level can be maintained more constant than they're currently being maintained on the grid. So, because it turns out that all of the software and hardware and measurement and everything is already been, it exists already for keeping the substations happy. So anyway, there are these challenges, but people know what they are, and they've been working hard to solve them. And they're pretty well, the solutions are well at hand. So what's going to happen to the grid? Well, right now we've got, basically we generate it, goes to a substation, and it goes to small loads in various places from various substations. And maybe there'll be a substation with a really big load on it, of a big factory or large shopping center, something like that. But where we're headed is something more like this. And you can see the point here. Starting on the right-hand side, got a big load, a shopping center, but they may have a relatively small photovoltaic system. When I say small, in this context, I'm talking about in the hundreds of kilowatts, and small storage, meaning in the hundreds of kilowatt hours. But then we move to a residential situation where we have baby PV systems, and a baby PV, we're talking in the neighborhood of 10,000 watts, and baby storage, and again, we're talking neighborhood of 20 kilowatt hours. And some loads will have only storage, some will have only photovoltaic, some will have both. Then we move back to the substation, and there may be some storage at the substation to help stabilize the power at the substation. And there may be some larger renewables at the substation. And then we move on to the generation, the major generation, the hundreds of kilowatt hour or hundreds of kilowatts. And there we need to be really careful, because you notice the generation has to only come out of that orange or that pink box, whereas substation can go either way. But that bidirectional link is really important to make sure, and that big storage and big renewables. And utilities are already doing it. A lot of states. Florida has a huge energy storage system that Florida Power and Light folks have installed, and some huge renewable fields. So this is where we're going. You can see the kind of engineering that might apply to your particular background. And then there's the part about government leadership. And protests are part of government leadership, as long as they're nice and peaceful. And because that's how people in government sometimes get information from the public. And these are all things that can be done in government. And some have been, the military understands that it's to their advantage to go green as much as possible, because moving fuel around is very costly and dangerous kind of an activity. So what government could do is have incentives for zero energy renovations and conversions. Now, the other part is investments. Where does money go? This is getting into the ethical part. And last year means a few years back. This is one of the slides I didn't update. This applies to 2022. So that the year that's in more like around 2000. But if you don't like that, sometimes you might protest. Because there are some institutions that don't invest in fossil. And I'm not saying I don't like fossil fuels. They're very important right now to make up the difference. But in the long term for the planet, it's pretty clear that the current use of fossil fuels is not a very smart idea. So we need to do something. Now, here's the kicker. Here's the last thing. What is the effect on the gross domestic product? All right. If we don't change the way we're doing business, or we do aggressive action. Aggressive action simply means following the Paris Climate Accord. Okay. And here's the study that was published in Scientific American in 2019. Okay. And look where we are. United States. If we don't get on the ball, we might see as much as almost 14% decrease in per capita gross domestic product, but the most likely decrease will be 10%. China, if they don't follow the Paris Climate Accord, they lose less, but it looks like China has already understood that they are going to follow the Paris Climate Accord. And most of the other rich countries in most of the world will be following it. So where does that leave the United States? Well, this is what the economists say. So let's check the time. 11:35. My goodness. Is there more here? Oh yeah, I forgot. Sectors most affected, significantly affected. You've seen pictures like this, the agricultural sector, some of the costs of not going green. 2019 flooding, loss of more than $2 billion in Iowa. Drove through Iowa just a week ago, and a lot of farmland there and a lot of corn there. And what a shame if they had extreme flooding. The National Oceanographic and Atmospheric Administration estimates the Midwest could lose up to 25% of their corn production and their soybean yields by 2050 if we don't get on the ball. National Academy of Science, 5 to 15% overall decrease in crop production for each degree centigrade average temperature rise. Pretty careful scientific studies by these folks. In the infrastructure, flooding damage, trillions of dollars in losses. Ask the people in Asheville. Housing, airports on the coast, docks, railroads, all that stuff. Wind and fire. Yeah, ask the people in Los Angeles about this. And you know, where's this reflected? Well, it's reflected in insurance rates, whether or not you can buy insurance. So pretty important stuff. So effectively, that means every sector is affected because everybody wants to buy personal property insurance. And that includes flood insurance, wind insurance, weather insurance, and so forth. And then there's the greener ethics part. Let's take a look at what that might mean in terms of ethical. Well, one thing that's interesting, if you look at either the ASCE, IEEE, ASME, NSPE, all of these professional codes of ethics include a statement about the responsibility of engineers to the planet. So engineers, at least the organizations are on the ball, are adopting these in their codes of ethics. CO2 production, it can be profitable, it can be cost effective. Why not make a profit doing something that's good for the planet? Last year, the increase in jobs in renewable energy, in clean energy, and that includes energy efficiency, was something like 50% higher than the average rate. That may change this year. I know the company I work for had to lay off a lot of engineers because people are now looking at what's going on out there. But the possibility is there for millions of new jobs in clean energy. And you know, our job as design professionals is to convince the clients that what we're proposing they do is cost effective and it makes sense and they're going to be happy with it. And it's part about reminding that green reduces healthcare costs and a whole lot of other associated costs. Look at the healthcare issues associated with people that, with just respiration, with all the smoke in the air. But it's more than that. These energy recovery ventilators and so forth, in terms of fresh, clean air, inside air can be really nasty in terms of the health of the people. So if we look at reduction of healthcare costs, we could call that an externality maybe, but none of this has been factored into the economic analysis we've done up to this point. But they're all there. They're well documented. So bottom line is now's the time to act. Gross domestic product may or may not be an acceptable way of measuring the health of the planet. But one accurate measure is greenhouse gas concentration, because we have pretty well established that the higher it gets, the less healthy the planet gets. And fortunately, we can afford it. And others are doing it. And we are doing it and have been doing it, and whether we'll continue remains to be seen. But we can't say that when all is said and done, a lot more is said than done. That's not good enough to just sit there and talk about it. Because children, grandchildren deserve more than that. And I just visited and attended my great grandson's 5th birthday. He will be 80 years old in the year 2100, and I would like for him to have a planet he can live in, which is why, even though I'm pushing 82, I sit here talking about this material because I want to leave and be a part of leaving a legacy that the people in the future will say thank you. So this finishes the presentation, but we do have time left. And in fact, we have 20 minutes left. So anything you want to talk about, I would encourage you to open up your microphone or type into the chat box, whatever you like. Or, yeah, I'm going to open my chat box now in case anybody has anything. GDP is expenditure. Okay, well, that's good to hear. I didn't realize that, John. Thank you for sharing that. That global crop yields are at record levels. Building mass to store heat. Oh yeah, that's happening a lot. That has been happening for a long time in the Southwest. The massive buildings to store heat for the cold nights where there's a big diurnal temperature variation. And yeah, that, I mean, obviously, I didn't cover every possible situation. You can't do that in a short presentation. So you need to do the math on everyone to see that it worked. What interest rates? Let's see, John, I'm not sure on interest rates. When you say what interest rates, maybe you could either open your mic and explain, because yeah, there are a lot of different interest rates, and I don't remember now which ones I may have been talking that you're asking about. Okay, what defines an array? All right, how many panels? Well, an array could be one panel. An array simply means the total number of panels that are used in the system. Okay, so typical array that I see has somewhere between, say, 30 and 70 for residential applications, between 30 and 70. And I'm going to call them modules because panels once had a different meaning. Panel used to be a collection of smaller modules, but now a panel is generally accepted as an individual module. All right, so let's see. And yeah, GDP, well, gross domestic products is what we spend, yeah. So in order to spend it, we have to earn it. And some of the expenditures are for food, healthcare, and other things like that. So maybe there's some meaning, and it's what they've come up with, and there may be a better way to measure, as we suggested. Gross domestic comfort, gross domestic satisfaction, gross domestic compassion, whatever. Who knows? Different countries would interpret it different ways. Let's see, Richard, what about building mass? Got it. Mitchell, hotels and apartments with limited roof space compared to occupancy. Yeah, well, this hotels, apartments, and so forth. Let's include condominiums here because that's what I live in, and indeed, we don't have a way I mean, our roof is so cluttered, there's no way we can put on, and furthermore, we live on the ocean and 130 feet above sea level, and exposure D is an incredible over 100 pounds of per square foot of uplift pressure. So there are places that can't practically include photovoltaics or solar water heaters. And but hotels and apartments, if they have roof space, whatever they can do is useful. Um, but shopping centers have these huge flat roofs usually, and they can put a whole lot of, and oftentimes industrial facilities and warehouses and stuff like that, they have lots of room. The condominium next to me has canopies over their parking areas, and they would work just fine for photovoltaics. So, but there are places where PV is not practical. There are places where wind is not practical. So yeah, let's see. I have to go back to slide 21. Oh, for replacement of natural gas generation, what is slide 21? Let's go back to slide 21. Hold on. How can I go backwards? There we go. Tell me when I'm on slide 21, okay? I'm not counting. 21 for replacement. Oh, okay, I know which one that is, you mean. I think this is probably the one you're referring to. And the 918 million kilowatts goes back to the capacity uh, of the natural gas capacity. There's 1.47 trillion kilowatt hours we need to replace because that was the generation due to natural gas. And you know what? That might be a few years ago. Let's see, what is it in some of these numbers may not compute exactly. The point is, we're looking at mostly order of magnitude. Partly, for example, even using photovoltaics now, the number is more like $1 per watt or per kilowatt hour of replacement. And here we were using a larger number than that based on an earlier cost of photovoltaics. So the natural gas generation replacement, I would encourage you, John, to get the 2025 numbers if they're available. And the calculation is pretty straightforward. Recognizing, but used for the renewables, $1 per kilowatt hour replaced. And that comes very close to the present cost of either wind or solar. Let's see, what else have we got? Indirect. Okay. Got Ed's answer. Climate change economics, yes. Okay, is there anything else I'm missing here? An array, okay, we've defined that. I mean, an array in a utility field can be thousands of panels, thousands of modules. In fact, it could be 1,000,000. 400 megawatts of 400-watt panels would be 1,000,000 panels. Takes a pretty good workforce to install those. But there are some fields that big, and people say, oh, what a waste of land. Well, compared to if we want to rip up a freeway and do something else with it, that would be pretty costly. If we want to rip up those 100-megawatt solar installations or wind installations, solar in particular, you take down the panels, you unscrew the ground screws, and you walk away, and it's as though nothing happened. And you recycle the panels or you do whatever. But in any case, the land is useful and available for other use at a relatively minimal preparation cost. So, one of those little mythologies that are out there. Okay. Oh, John, what interest rates? That's the one that we're still trying to get at. Have you, let's see if I answered that question. Okay, your question was slide 21. Okay. Anything else? Oh, 2 new messages. Yeah, and of course, the economics, John, that gets really interesting because that's, once again, trying to predict the future and what's going to happen with the discount rate and what's going to happen with the interest rates and all that sort of thing. And that's, well, certain people are trying to get the Fed to reduce the interest rate. The Feds are sticking to holding to where they are right now. And so usually it's easiest to get a rough order of magnitude idea by assuming the inflation rate and the increase will be about the same. And then it sort of goes in constant dollars. For example, the cost of photovoltaic since 1970, back in 1970 was about $300 a watt in 1970 dollars. Right now, the price, if you buy them outside the United States, say in South America, is about 19 cents a watt in $25. So the cost has come down by a factor of about 500. And John, you're also right. I mean, if you really want to do a fancy analysis, plug them in. But again, you can't do it without making an assumption about what's going to happen in the future unless you have a fixed interest rate on a loan. Then you can know what your payments are going to be. But in terms of inflation, that's something that very difficult to predict. So there are a number of different options you can use for doing a financial analysis, and net present value is one of the more useful ones. Okay. Oh, and here's the host. Says, I can end. I can shut up. We can go eat. Okay. Thank you, everybody. I hope something useful may have been presented. And note the log on for the site if there's anything you need. All right. So time for me to stop sharing my screen and to sign out.